Hey guys, today we're going to be working on slope fields. This is 9.3. And slope fields are really just these little graphical representations here of differential equations. So you can see an example right here on the right. You can see an example if you flip through these other pages here. But we're going to work on doing a couple different things with them, such as creating a slope field on the table below, or learning how to recognize a slope field and matching it to its equation. All right, so some different things that we'll be looking at. For instance, in this one right here on the right side, you can see that all of the little slopes going across are the same. Now, just like a line that would run horizontally, this means that it must be based on y alone. So that means my differential equation, dy dx, would be equal to something that's only based on y, and that's what you can see right here. So that is this differential equation here. All right, so what we're going to do to learn how these work is we have a table here on the left. So if you don't have one, you can always create a table, and we're going to plug in some things. So my equation here is only based on x in this problem. So you can see that dy dx is equal to 3x minus 2. So looking at my table here, I have x values of -2, -1, 0, 1, and 2. So I'm going to plug those 5 values in to my chart here. So -2, -1, 0, 1, and 2. And we're going to calculate what slope we would get from that. So if we plug in -2, then we get 3 times -2 minus 2 is -8. 3 times -1 minus 2 is -5. Okay, and we just keep going. So 0 minus 2 is -2, 3 minus 2 is 1, and 6 minus 2 would give us 4. So what this is saying is that when x is -2, so that would be for all 5 of these values here. When x is -2, my slope should be -8. So what I'm aiming for here is to make a line whose slope is -8. So you kind of have to imagine creating a slope of down 8 over 1 and how steep that would be, and making a line with that slope. So you want to try and make sure it doesn't look like it's straight up and down, although it almost would appear that way. All right, so our next one, when x is -1, we should have a slope of -5. So again, if I went down 5 and over 1, it would look almost just as steep, just a little less so. Okay, and then we move over when x is 0, a slope of -2. So now we'll start to notice more of a difference. Okay, when x is 1, we have a slope of 1. So notice now how it switches from negative slopes over to positive slopes. So things like that are always good to notice. Slope of 1. And you're just making a little tiny slope of a line. So imagine a line with that slope the entire time. Okay, we're just going to make a tiny little line segment. That's what we're doing. When x is 2, a slope of +4. Okay, so attaching that here. Steep again. And there we go. So we've created our own little slope field. So you'll also notice again that, like the example above where everything was based on y, so all the lines horizontally were the same, now you'll see vertically that they all appear to be the same slope. These are all the same, and that's because it's based on x. So you'll run into some tricky problems when your slope field is based on both y and x, like in example 2 here. So this one will take a little bit more time. So what we're going to do is fill in our table of values and then create our slope field. So we'll use values like when x is -2, -1, 0, 1, 2, and then y. So I don't have a table big enough for all the different values. So hopefully what we'll do is start to recognize some sort of pattern. So it might be easier to start with the positive values. And then we also want to take our differential equation here and solve in terms of dy dx. So that would mean we would subtract 2x and then divide by -y. So we're left with 2x over y. So some interesting things we can actually get from this. First of all, when x is 0, dy dx will equal 0, except in the one case when y is 0, bad things happen, right? Can't divide by 0, so dy dx is undefined. And so typically we just don't have anything. So when y is 0, that would be the x-axis. That's the line y equals 0. So along the x-axis here, the slope is undefined. So we could register that as a vertical line slope, or we could really just not have anything there. It's okay to do that as well. So vertical lines or no slopes here. And then when x is 0, that's the y-axis. When x is 0, we're going to have a slope of 0. So that would be little horizontal line segments for these 4 values. So real easy. We're just left with 4 values in each of the other quadrants. So let's go ahead and start with when x is +1. We have 4 different times when x is +1. So our 4 different values for y, we've got +2, +1, -1, -2. So we're just going to plug these values in and calculate our slopes here. So at 1, 2, we have a slope of 1. At 1, 1, a slope of 2. At 1, -1, a slope of -2. At 1, -2, a slope of -1. Okay, and then I'll do the same here for x is +2. And fill in the y values. So we'll run through the same y values, 2, 1, -1, -2. So at 2, 2, we have a slope of 2. At 2, 1, a slope of 4. At 2, -1, a slope of -4. And at 2, -2, a slope of -2. So now we're going to go over and record the slopes here. All right, so you can see that I've already come over here and filled in these 2 quadrants for the values that I had. And I started to notice a little pattern when I was doing this, that along the line y equals x, I had the same slope. So right here at 1, 1 and 2, 2, they both had a slope of 2. You'll notice this will continue into -1, -1, and -2, -2. If you plug those in, they'll just reduce and leave behind a 2. So I'm going to have the same slopes on those values, which means that right over here on y equals -x with a slope of -2, these will all have a slope of -2. So little patterns like that will help you to fill in the table a bit faster. And then what we're looking for is just the remaining slopes here. So at -1, +2, we're going to get a slope of -1. Which was opposite of what we had over here. So we're likely just going to continue in this same pattern. Slope of 1 down here. At -2, +1. Okay, we'll have our -4, and down here at +4. Just to finish filling that in. The next thing is it asks us to use integration to solve for the general solution to this differential equation. So we've done this before. We're going to take our equation here and I'm going to separate my variables, so I kind of did that already. I just need to finish. So we're going to take this equation and multiply y over to the left, so y dy. We're going to keep our 2x and multiply dx over to the right, so now it's a dx here. So now we're ready to integrate. So we get y squared over 2 is equal to x squared plus c. So you'll notice you have x squared and y squared, which means that we're looking at some kind of conic. So let's get y squared by itself. Y squared is equal to 2x squared plus c. And then if we knew an initial condition, we could solve for c without it. We're just going to leave c as part of the problem. If we need to get y by itself, remember when you square root, definition of square root of y squared, we're going to get plus or minus the square root of 2x squared plus c. All right, so that is the equation of a hyperbola. If you'll remember standard form, typically with hyperbolas, we would get x squared and y squared on the same side. So you can see that minus sign is going to tell me that this is a hyperbola of some kind. And that's what I was seeing in the picture of the curves. Okay, so some kind of image running through like this. And without an initial condition, we don't really know where the lines go. So this is just an example of what it could be. So our differential equation now for dy dx is negative x divided by y. So it's based on both x and y, and once again, it's just the ratio of the two things, leaving behind a negative. So when I am working with these 4 points here, I'm working in quadrant 1, quadrant 2, quadrant 3, quadrant 4, and you'll notice they're all 1s, just positives and negatives that rotate. So the value of dy dx in quadrant 1 is just going to reduce to negative 1. But in quadrant 2, 1 over 1 is 1, but I now have 2 negatives, so it's back to positive. Quadrant 3 will have 3 negatives. In quadrant 4, we'll be back to 2 negatives. So we're going to be back to an answer of 1. So the slope is positive in which quadrants? So 2 and 4. And negative in quadrants 1 and 3. All right. Down here on part B, for the same thing, compute dy dx at these sets of points. So what do you notice about all of these sets of points? Their y value is 0, and when y is equal to 0, we're along the x-axis. So 1, 0, let's see, we get negative 1 divided by 0, or 2 divided by 0, or any time we're divided by 0, we get a value of undefined. Okay, so write an equation that would describe the slope as undefined. So that would be actually what I did right here. It's just y equals 0. Okay, when would the slope equal 0? So when would dy dx equal 0? So remember, dy dx is x over y, so we would get a slope of 0 when x is 0. Okay, and so that is the y-axis. And y equals 0, that is the x-axis. All right, so for the same one, we want to consider these values. So you'll notice that all of these lie along the same line. That would be y is equal to x. So when we're on the line y equals x, we get negative 1 divided by 1 is negative 1. Negative 2 divided by 2, negative 1. Opposite of negative 1 divided by negative 1 is negative 1. And same thing here. They're all going to be negative 1. So what equation would express the slope as negative 1? Y equals x. And so how about a slope of positive 1? So we would be running along y equals negative x. Just adding another negative to make it positive. Okay, so using the grid at the right, we want to sketch the slope field for the values calculated for parts A, B, and C. So we're going to go through now and start making those. We're going to start here at the undefined values actually would be best. So y equals 0, the x-axis, undefined. So again, you can do your little vertical lines or you can have nothing. Either is fine. Then we'll go in and add in on the y-axis, horizontal lines, x equals 0 is the y-axis. Here we go. And then we've got y equals x along y equals x. Here in quadrants 1 and 3, we're going to have a slope of -1, okay, -1. And then on y equals -x in quadrants 2 and 4, we'll have slopes of +1. So this will take you a little bit of time, but we need to go in and finish filling in the rest. So I will walk you through a couple of these points. You're going to look for any other patterns you might find to help you fill it in a little quickly. So at 1, 2, if we plug in x is 1, you might make a table again if you want, x, y, dy, dx. So when x is 1 and y is 2, my slope would be -1 over 2, so -1/2. So right here we want a slope of -1/2 of 1 over 2, so about like this. Okay, and then we would do the same 1, 3 would be -1 over 3, so even more steep. And we just want to continue that, so let's try over here with 2, 1. So that'd be -2 divided by 1 is -2. So what about 3, 1? That'll just be -3. Okay, a couple more. So we'll do 2, 3 is -2/3. And then 3, 2 will be -3 divided by 2. All right, so go ahead and finish filling in the rest of the slope field. So now that we have a finished slope field, we're going to continue on with part E, which asks us to draw the particular solution that passes through the point 0, 2. So we're going to come up here to the point 0, 2, and we are going to follow our slopes around here. So as we get to the next tangent line slope, we're just going to start curving with it. So just follow the slopes all the way around, and you should have been able to see what looked like a circle, right? All the rings coming around here. This is just the particular solution. So now we're going to solve the particular solutions. We want to solve the differential equation. We're going to start with our differential equation that we were given. -x over y. We're going to separate our variables, so multiply y over to the left, multiply dx over to the right, and then we can integrate both sides. So on the left side, we'll end up with y squared over 2. On the right side, -x squared over 2 plus c. We're going to go ahead and multiply by 2 everywhere. Y squared is equal to -x squared plus c. And at this point, you can use the initial condition to solve for c, which is the point 0, 2. So we're going to go back and use 0, 2 here. So when we do this, we have now 2 squared is equal to 0 squared plus c. So c is 4. And we can go back over here. Y squared equals negative x squared plus 4. Okay, the equation of a circle, we should have x and y squared on the same side. So this is the equation of our circle here, or we can solve for y. So y squared, 4 minus x squared, and square rooting both sides. Y would be plus or minus the square root of 4 minus x squared. Okay, so in this section, what we're going to do is try to match our differential equation to its slope field picture. So I'm going to start by giving you a couple of ways that we'll know what to do. So some things that you'll look for are, is it all in terms of x? If it's all in terms of x, remember, like an x equals line, then all of the vertical lines will have the same slope. Or is it all in terms of y? Then all the horizontal lines will have the same slope. Sometimes an entire quadrant is all positive or all negative slope. Or you might notice lines where the slope is 0 or undefined. This one here, number 1, is only in terms of x. Number 2 is only in terms of x. Number 4 is only in terms of x. So there's 3 of them that are only in terms of x, which means there are 3 graphs whose vertical lines all have the same slope. So I can see that in A, all the vertical lines here. These are all the same slopes if you just follow the graph up and down. Right, you can see the same slope running through it. So there's a couple other graphs that do that. Okay. Let's take a look down here at H. H does that. Right, so you can see some 0 slopes right there. Okay, and I can see that also with graph D. Interesting thing about the graph for part D is that it doesn't have any slopes over here at all. So past some negative value, it doesn't exist. So let's take a look here. Number 4 is a cosine function. It should exist for negative values there. As we compare 1 and 2, it looks like number 1 is not going to exist when x is less than negative 2. So this is going to be graph D. Right? So looking at the other 2, remember dy dx, here the slopes are x times e to some power compared with dy dx is equal to cosine x. So we can see on graph H what almost appears to be a trig function running through here. So that's going to be the graph for number 4, leaving A to be number 2. Okay, so maybe now we'll start looking at the ones that are in terms of y. So only in terms of y, number 5, number 6. So just two graphs. So this means that all the horizontal lines will have the same slope. So I can see that here on graph C, right? Those are all the same. I also notice all of these slopes are positive. They're all positive. On E, I notice same thing. And then they switch right here. They suddenly become negative, and then they don't exist for any negative values for Y. So in comparing those two things, number 5 should match to E because we can't take the natural log or log of any negative number. So that's going to leave number 6 as C. Notice Y squared, always positive, add 1, always positive. So this is the graph for C. So with the remaining ones, you're going to have to look at some different things going on with them. So they're all in terms of X and Y. On graph B, you'll notice that in quadrant 1, all the slopes are negative. All the slopes in quadrant 2 are positive. All the slopes in quadrant 3 are negative. All the slopes in quadrant 4 are positive. You've also got a slope of 0 running along here, right? When x equals 0, x is 0. And then I don't see anything running along the x-axis, y equals 0. Possibly got some undefined values there. All right, so on F, we've got, again, what could be some kind of curve here, right? But we've got these certain slopes here that are just all negative running through it as well. Okay, and on graph G, you can kind of see the curve there happening again, but it kind of just goes off here, curving, okay? So all of these slopes, we've got negative and it switches to positive. You've got a couple of little horizontal slopes in some places here. So let's try looking instead at the equations. Number 7 says negative x times y. So this should tell me that if I take the product of my negative and the value of x and the value of y, it'll determine the value in each quadrant. So in quadrant 1, when x and y are both positive, I would have a negative product. In quadrant 2, where x is negative and y is positive, I would have a positive. And so this is what was happening in the graph for part B. For the remaining two, they're both trig functions. So maybe we'll look at the functions and determining their values. So let's say this is x plus y. If x and y are opposite, if they're opposites, then this will add up to 0. We'll end up with cosine 0 is equal to 1. So anytime we're on the line y equals negative x, we should have a slope of 1. So we're looking at y equals negative x, a slope of positive 1, and might be able to go back in here and see if I can see that here. So along y equals negative x, would be right around here. So do we see a slope of positive 1 here, or do we see that over here on graph F? And that is what I see on graph F. Those are slopes of 1 right along that line, which means graph G should match up to sine y plus x. So just looking at maybe some values like sine of 0 is 0. So anytime y is 0, we're on the x-axis. So that means that the x values, x-axis values, are just going to depend on x at that time. So looking here, so anytime you add 0 to a number, So if x is 1, you get a slope of 1. If x is 2, a slope of 2, and so on. So that is what it looks like here. So a slope of like 1/2, and then it becomes 1, and it's getting steeper as it goes out and more negative as it goes into the negatives. So that is going to be our last graph. In this last example, a differential equation, a point, and slope field are all given below. We're going to use the slope field here on the right to sketch a particular solution through that point. So we're going to take the point 0, 1. We're going to plot it over here. And we want to draw the curve. So imagine we're just throwing this little needle into a stream that is running, and we just want to follow the curve of the stream. So where would this needle go? So out to the right, it's just going to follow these little slopes out here this way. Okay. And then as it goes to the left, it looks like it's going to start curving pretty sharply. You'll notice the slopes abruptly change from positive to negative. So right in the middle here, it should be passing through at -2, a vertical asymptote. So it's likely that we are not going to go past that, but just follow it out rather. And down. So this should be our curve. So if I were to solve now my differential equation, I should be able to come up with the solution. That would be this graph. So in separating my variables, we're just going to multiply dx over to the right side. And then we're ready to integrate this. So if you like, you can use your u substitution here on the left. Let u be x plus 2. You'll see that your derivative there is just dx. So this becomes 1 over u du that we're integrating. All right, so we now have y is equal to the natural log of the absolute value of u plus c. We'll replace u with x plus 2 plus c. And now for the initial condition. So I'm going to take 0, 1 and substitute them in for x and y here in the problem. So y is 1, natural log of 2 plus c. So c is 1 minus the natural log of 2. And that'll just go right back here into the problem. So we have y is the natural log of x plus 2 plus 1 minus the natural log of 2. And that'll be my equation.